So I'd like to thank the organizers to give me for giving me this opportunity to present our work, and it's a special honor to be here celebrating Shriram's illustrious career, for which all of us came together. So this is my name, Debashish, and I work in Institute of Physics, Bhubaneswar, which is in the eastern part of India. So I'll be talking about these two topics of recent interest, inertia and in some sense reciprocity and particularly additivity in active matter using a couple of different model systems. Okay, so just to set the stage, what I have in mind is some kind of, so for the first part of the talk, what I have in mind is some kind of self-propelled active Brownian particle systems, which has a persistence, which undergoes a persistence motion under the self-propulsion. And this, okay, so, so if they come together, then we know that they can undergo at given amount of activity and density, they can undergo motility-induced phase separation, etc. So that's one kind of systems I have in mind. The other kind of systems, and then if they are sort of slightly bigger in size, they may have inertia. I'd like to probe the impact of inertia, possible impact of inertia on single particle and many body level. So that's the first part, and if time permits, I'll also consider impact of these reciprocal interactions in a model apolar active pneumatic systems. Okay, so there's a list of papers on inertial work. So I don't see, okay, yeah, I can see it now. So some of the work is of course like Shriram's work and others. And of course, so let me just begin by giving a little introduction about the inertial effect on motility-induced phase separation in active Brownian systems. So what was found somewhat recently that we know about this motility-induced phase separation, in which if you take active Brownian particle systems at a high enough activity and reasonable densities, they can undergo phase separation in just presence of repulsive interaction between the particles. But what happens is that if you incorporate inertia, which will give rise to an inertial timescale m by gamma, and this over this inertial timescale, if the inertial timescale is large enough, so here a phase diagram is shown, what happens is that the motility-induced phase separation disappears. So this has some kind of like active kind of behavior is going towards a passive kind of behavior if you increase inertia, and the this value, this is the inertial times. So this value is a ratio between the inertial time scale and the persistence time. So you see that if the persistence time, inertial time scale is like more than 7% of persistence time, you lose the full effect of motility-induced phase separation. So this was observed. Then what we are asking is that if I take a system which is at low enough densities, so it will not be able to undergo motility-induced phase separation, is there any particular signature of inertial effects in the late time dynamics of the system, particularly individual particles which are in this bath of other particles? So that's the particular question I'll try to answer in the first part. So what happens if we particularly took an extremely low packing fraction system in which the system will not undergo phase MIPS, and what we first try to see, what is the, so in the dynamics of individual particles, what is the impact of this interaction between particles and inertia? So what happens is that, so in these two graphs, what I'm trying to show is that if you take really an extremely low inertial value, m 0.01. So that limit, the system behaves almost like a individual particles will behave like a overdamped active Brownian particle. But in presence of repulsion, of course, even that system will show a, so if I look at a velocity distribution of this particle in the active orientation, so that's V parallel. So a free particle should show a distribution which is peaked at the Peclet number for that particle, but in presence of collision that will show a long tail, so it's getting collided and one can get velocities which is backward direction as well, so negative values, and this one can understand in terms of the pair distribution function, which shows strong asymmetry between the front and back for the overdamped system. But as you see that if you increase inertia, so this amount of asymmetry starts to decrease with that. So if I just plot the this amount of asymmetry by subtracting the front peak, back peak from the front peak, this quantity. So you'll see that this quantity for large enough inertia, it slightly increases and then it starts to decrease with increasing Peclet. So what happens is that because of this inertial recoil, so first a particle can go and bounce from a particle in front, and because of inertial recoil it can go back and get a back collision. So this effect was absent in the overdamped limit. This becomes prominent as you increase inertial time scale with respect to the persistence time. So, but that's individual particles dynamics, and then that leaves a long time effect in the late time properties of the dynamics of these particles. So what we do here is to look at these three quantities, particularly the kinetic temperature, the effective diffusion, late time diffusion constant. Of course, all these particles one can calculate the mean square displacement, which will ultimately at late time will show a diffusive scaling. So the late time diffusion constant and the mobility of individual particles in this dilute bath. So what happens? First, let me tell you the results. The kinetic temperature, so overdamped limit results we knew. The kinetic temperature should go as Peclet square. The effective diffusivity should go increase as Peclet square. But what happens that if you increase inertia, so this, for example, the effective diffusivity starting from Peclet squared, extremely small values of inertia, increasing values of inertia, this becomes a function of mass, the exponent, and finally you get a scaling which is more like a linear in Peclet behavior. So these behaviors we can roughly account for using a kinetic theory argument, and as well as doing exact calculation for single particles, free single particles and single particles in trap. So I'll just show that in next slides. So what happens is that the kinetic temperature for single particles, if I calculate, that shows a behavior which looks like the kinetic temperature will grow and saturate. So in presence of repulsion, I have an extra correction which depends on density and the collision frequency, which depends on the collision cross section. So this quantity. This quantity, the collision rate, which depends on the collision cross section and a typical scale of velocity, which here is governed by the Peclet number. So this is how we typically do our kinetic theory even for equilibrium systems. There, instead of Peclet number, one would have used the mean square velocity, and then it will depend on temperature. So here, that role is played by Peclet. So what we do is that one can get the one can get this effective cross-section, collision cross-section by equating the kinetic energy and the potential energy of the system of these particles. So for the free particle, this is the kinetic energy, mean kinetic energy expression, the derivation of which I'll show later. And in presence of any potential energy, if I can write that as a single power law, one can equate them and get a length scale where these two things balance at collision, so which will give me the collision cross section, and I put that together to get the collision rate. And then these two things together also gives us the mean free time, which is given by the, of course, mean free path and the Peclet number, which can be written down as 1 divided by the density times the collision rate. Okay. So the one reason why I'm writing this down, this kinetic temperature, effective kinetic temperature, this is not a derivation. So I'm reasoning it using a exact calculation for active Brownian particles in a harmonic trap. So if I do the kinetic temperature calculation for that, so this calculation is done in general D dimension. What you see is that, so this D is for the dimensionality. What you see is that this beta, this number, this stands for the harmonic traps, trap strength, or the relaxation time, inverse relaxation time of that. So if I replace that inverse relaxation time, so what I'm doing roughly is that assuming that a single particle in a harmonic trap is sort of like a behavior of one particle colliding with another particle which is static. And using that reasoning, I am replacing this inverse time scale by this quantity, the collision rate, so the mean free time, rho times pi c. So this reproduces one behavior which was seen before in the calculation for active Brownian. So the MIPS calculation, two-phase coexistence showed that high density regions will have lower kinetic temperature than the low density region. So that can be explained by that. And of course, these quantities together can explain. So this is one, that part is for the kinetic temperature, and the diffusion constant can be written down as in terms of the mean free path and the Peclet number, which will, in the two limits of small and large mass, shows us these possible behaviors of Peclet square and linear scaling with Peclet. So, and the mobility will always go down as a function of mass. And at large mass, it will also go down as a function of Peclet, linear, 1 by Peclet order. So these are these behaviors we have, particularly these are too many results. Maybe we can just focus on this, the active diffusivity goes from a Peclet square behavior to linear in Peclet behavior, which is this result. Okay. So, and then one can put them together and try to see that a measure of, with increasing inertia, how things can return to equilibrium, just looking at the difference from the equilibrium fluctuation dissipation kind of relation. So this quantity, since we know d effective kb, all these three quantities, one can calculate that this departure, and this departure really goes down as a function of m. And here it's a argument by which we wrote down these results, but for free particles one can exactly derive this departure. And also for free particle also, what happens is that at large enough inertia, this second term will approach 1 and this I will go to 0. This departure will go to 0. Okay, so quickly I can show what happens with the free inertial ABPs. So one can write down the Langevin and Fokker-Planck equations, and then from that can write down an equation governing the mean variable in the Laplace space. So this one can take like that master equation, and whatever observable you have in mind, you can put that observable here and do this calculation. So we did several calculations. I'm showing 3-4 of them. So one is for free particle, what is the uh, effective kinetic temperature, which shows a mass dependence in d dimension. What is the diffusivity? So in absence of interaction, diffusivity is independent of mass. That's the most interesting behavior. So diffusivity became dependent on mass for interacting active Brownian particles in presence of inertia. And this departure one can calculate, and also one can get an exact expression for the swing pressure, which also decays as a function of mass, and large enough mass will go to 0. Okay, and this system also shows some interesting behavior that if you can also calculate all other higher order moments and can show that the velocity distribution of these particles will go from a Gaussian-like to a non-Gaussian and back to a Gaussian behavior as you increase inertia. So I can quickly try to explain that. What happens is that for a single particle at very large values of inertia, there will enough time during the inertial relaxation time for the persistence to lose its direction. And as a result, you get an effective equilibrium-like behavior and you get a Gaussian distribution. So that's the distribution shown here. So I'm pointing 0.4, this point. So this value of inertia and Peclet. So sorry, I mixed up this symbol. So lambda is Peclet here. And if you look at this regime, there it's a completely non-equilibrium behavior. You see this ring pattern of the velocity distribution. And this ring pattern is maintained by, if your m is small, then of course like you have a specific direction in which the velocity goes, and this peak is at V0 or the Peclet number. And of course, if you decrease m, then what happens is that this radius shrinks to small enough values that if your thermal background fluctuation is bigger than that, you'll again go back to equilibrium-like distribution function. So these are these distribution functions and some expressions for that, simulation results and these calculations. And then, as I suggested, that inertial active Brownian particle in harmonic trap if you look at that, it gets a dependence on, so the kinetic temperature depends on the trap strength, that inverse time scale, and effective diffusivity also depends on this trap strength and inverse time scale and mass. So this could be a possible direction through which things in the interacting particles, diffusivity becomes inertia dependent. But it's not a full calculation, one needs to do a full calculation. So in summary, what I showed is that in an active scalar path, inertia determines late time properties. Kinetic temperature, mobility, and diffusivity all depend on mass. For small masses, diffusivity behaves like Peclet square as known, and this changes to a linear in Peclet dependence at large enough inertia. And in free particles, we showed that the diffusivity is independent of mass and it starts to become mass dependent as even if you put the particle in a harmonic trap. So that's the first part, and I have 2-3 minutes, maybe 2 minutes. So I'll just quickly run through this. For this audience, I don't have to introduce what is apolar active nematics. I presume the apolar is that it flips the direction. So in my simulation particularly, it flips the direction. It chooses the active velocity direction along its orientation or the opposite orientation randomly. So that's apolar, and they align nematically. If they collide like that, they will align parallel, and if they collide like that, align anti-parallel. So that's the rule. So and eigenbeds models with the same symmetries typically are chosen out of convenience. So what we try to see is that if I use a reciprocal interaction, like some interaction derived from some kind of Hamiltonian, and compared it with respect to a rule in which an active particle just orients with its local neighborhood, independent of the number of neighbors. So is there a possible difference in the outcomes? Outcomes in the sense the many body large scale collective properties. So for this purpose, what we did is that we had chosen 3 models. Model number 1 is this Lebel-Lesher model with this Hamiltonian. So I purposefully chose not to write it sum over ij, should be sum over ij nearest neighbors, but trying to show that what is the interaction ith particle will face from the jth particles from the neighborhood. For that happens in a reciprocal model. So we tried to make a corresponding non-reciprocal version of that by just dividing the strength of this J by Ni, the number of neighbors instantaneously present in any instance for ith particle. So what this will do is that the interaction strength here will not depend. So here the interaction will depend on if I have n number of neighbors will scale as n. Here it will not. So, and the last model could be a non-reciprocal Vijaykumar-like model. So I have taken one model by Gushatis. So where local neighboring particles average nematic order is figured out, and this theta becomes the orientation of the largest eigenvalue of that quantity, and then you add a little noise on top of that, and increasing this value of noise, try to see the phase transition. So the difference between the first class and the second two are that in this mean field limit, for the orientational coupling, each particle sees a strength which goes as j times ni, ni being the instantaneous number of neighbors. Model 2, it doesn't depend on the total number of neighbors, and model 3 also, it doesn't depend on the total number of neighbors. It just figures out what is the orientation. The number of neighbors could be 100, could be 10. It doesn't depend on that. It depends on the orientation. So the orientational update, as a result, what happens is that this depends on the local density. And in these two cases, this is the main point I'm trying to point out. In these two cases, they are independent of the local density. So, and we choose this as control parameter for the transition. And the position is being updated following that rule. And we use a fixed active velocity. If you look at the outcomes are that the reciprocal model shows a clear first order nematic isotropic transition. This is the order parameter, this is the Binder cumulant, and the non-reciprocal model, for example, model 3 shows a clear continuous transition where from disordered to ordered phase, since the ordered phase is all quasi-long range order, they merge, all these Binder cumulants merge there. And what you see for this middle one is that if you take small system sizes, it suggests as if the transition is a first order transition. Then we increase the system size and finally see that what happens is that this typical negative maximum of the Binder cumulant characteristic of the first order phase transition that decreases and that starts to vanish as you increase the total system size. So, okay, so the idea here is that in general you have these coupled equations for the density and the order parameter field. But in the order parameter field, this ordering term, alpha 1 rho, that will depend on local density if you use the additive or reciprocal interaction. And that will be independent of density if you don't do that. So what happens is that alignment, of course, always couples, and if you get a orientational alignment, that will generate a phase separation. I'll just take a minute. And the other way around, whether this density fluctuation here will feed back to the orientational coupling, that depends on the choice of the model. If you take a non-reciprocal model, this is cut, this bond is cut. So phase separation does not influence the alignment. And as a result, aligning this guy alone will give rise to a continuous transition. But if you have this branch active, so this feedback works, then of course you'll get a first order transition because of this, which gets, so the feedback comes from this density correlation. Okay, and in the density field, of course, all three models look same. They show phase separation, and particularly this fluctuation dominated phase separation, and this giant number fluctuation in the ordered phase. And the ordered phase is quasi-long range order. So in summary, we show that so there are like one kind of reciprocity is that interaction reciprocity, and then there is a coupling between the pi field to rho field and rho field back to pi field. So if you have that or you don't have that, depending on that, you'll get either a first order transition or a continuous transition. So with that, we'll stop, and if there is a question, I will take.
I have one question to this first order phase transition. Is it similar to the using vector and scalar noise in Vijaykumar model? Because there also the density is.
Appears to me so. I've not worked it out, and I've not done the simulations.
So in that model, if you go large enough system size, then even the scalar noise goes.
So I can, okay, so one idea is this. I know, I don't know whether, yeah, Hugo will agree or not. So one idea is that in the original VCheck model, you orient to the local neighborhood. Just you have this orientation, and then you add the noise on top of that. So which is equivalent to saying that this interaction is independent of the number of neighbors. But for example, in the vector model, you take the orientation of each particle and take the noise of them, add them together, and then average them out. So which in turn what is doing is that it's taking that n, I am dividing by n not the first term alone, I am dividing by n the whole thing. So which then becomes like, this is a competition between the kind of entropy and energy contribution, if I say so. So then it's like an additive.
So in the final part where you showed density coupling back to
the order parameter.
But that is the mean field calculation for the linear term doesn't have the density. But of course, fluctuations can generate such a term. And I think recent work from Hugh and Solon and co show that at least with some versions of topologically interacting Vijayk or Vijayk style models do that. And I was wondering if you see any indication.
Yeah, so are you talking about topological interaction models?
Which is not dissimilar to what you have, right? You have the density independent aligning interactions.
Right.
And in the mean field case, yes, you don't have the back coupling of density to order parameter, but I wonder if you see evidence of fluctuations generating such a coupling.
Yeah, so if you have that coupling, then the fluctuations, what it does is that it's sort of also a calculation presented in one of Shraddha's paper. So if you have this coupling, then this fluctuation in density, that will feed back, and you can look at this current, and that will feed back to generate this cubic order term starting from this, so which leads to the continuous to the first order transition. So, but that's via this density fluctuation. So density fluctuation in the sense so the phase separation which is happening in that field. Okay, so I think I didn't respond to your question properly.
In general, you should generate by the same mechanism that Hugh and Cesare and others generate the term in polar systems, you should generate a density-dependent, A. I don't see how you can.
Thanks, Debashish.